Okay, so we had a little bit of a technical issue there that paused the video, but what we were talking about here is how many. So if we're interested in a combination, a five combination of five, we know how to count permutations, but how are we going to count combinations? We have to get rid of the ordering. So how we're going to start this is we're interested in the combination 1, 2, 3, 4, 5. So the numbers 1, 2, 3, 4, 5 in any order. And we're going to start that by saying, okay, let's assume we care about the order. And then if for any possible choice of five elements, the number of orderings is the same, we can just divide out the number of orderings. So what do I mean by that? Well, in this example, we know that 1, 2, 3, 4, 5, 1, 2, 3, 5, 4, 1, 2, 3, 5, 3, 4, etc. have all the same, well, all correspond to the same combination, which is this set 1, 2, 3, 4, 5 up here. Okay. So once we have the set of elements and we list them for to be definitive in increasing order from smallest to biggest, then how many different ways are there to order them from combination to permutation? Well, there are five different elements, and we need to consider all possible orderings of those five elements. That's just a permutation of five. So that would be divided by 5 factorial. Okay. And so this is actually, well, this is 2,118,760. Okay. But this is what gives us what's called a binomial coefficient. Okay. And we're going to define that here. So an unordered subset or collection of R elements of a set of N elements is called an R combination of N. And how many R combinations of N are there? Well, we write it as N R in parentheses. That's pronounced as N choose R. So from N things, we want to choose R of them. And the way that we choose R is we first choose them in order. So we first get an R permutation, and then whichever ordering we have, we remove the order by dividing by R factorial ways of ordering those elements. And this is equal to N factorial divided by N minus R factorial, R factorial. R combinations of N. N choose R is also known as a binary or a binomial coefficient. Okay. So what are some things to take note of? Well, in part B, what we notice is that the ratio of the event that we're interested in to all possible events is 1 divided by, so there's one set divided by 2,118,760. 118,760. Okay. So alternatively, we could play the same game as in A, but define the event in question as the set of all orderings of 1, 2, 3, 4, 5. Play game A, but ordered ticket containing 1, 2, 3, 4, 5 as a favorable outcome. Okay. So how many tickets are there? There are 5 factorial such tickets. That's 120 tickets. So in this case, number E would be 120. And we already counted the number of 5 permutations up here, which is 254,251,200. Okay, but this is 5 factorial divided by 50 fall 5, right? Which is 5 factorial, 45 factorial over 50 factorial. It's the same number. Okay, so they're both equivalent in terms of the ratio of the favorable events to the total events. So n choose R, this is the binomial coefficient n choose R. Okay. Something to be aware of is that n choose R is equal to n choose n minus R, and n choose R is equal to n minus 1 choose R plus n minus 1 choose R minus 1. We'll leave that as homework. And why these are called the binomial coefficients is because if we take a binomial expression x plus y raised to the power n, this can be written as the sum from j equals 0 to n of n choose j x to the j y to the n minus j. Let's do a second example involving poker hands where combinations come into play. So we're talking about 5-card poker hands. So we're assuming kind of traditional poker where there's a 52-card deck. Okay. Each card has one of 13 ranks. And one of 4 suits. Okay. And each card is a unique rank suit combination. Okay, so there are 13 ranks times and 4 suits. 13 times 4 is 52. Okay. We're not going to go into too much detail on poker here. You would need to know a little bit more to do it. We'd have to describe a little bit more how the ranks and the hands are defined. But we'll just do some simple examples here. So what's going to happen is you're going to be dealt 5 cards from the deck, and the value of your hand is determined by how those 5 cards combine. So for those who are actually familiar with poker, you may have heard of a game called Texas Hold'em. Similar concept, but a little bit more complicated in terms of how we would do this combinations. We're talking about kind of classic old school 5-card poker. You get 5 cards and that's it. So we're dealt 5 cards from the deck. So how many hands are there? So each hand, a hand is what I hold. My hand is 5 cards. Your hand is 5 different cards, and so on. So we're dealt 5 cards. So how many hands are there? So omega, the sample space, is going to be the set of all 5-card poker hands. How many 5-card poker hands are there? Well, don't overthink it. There's 52 cards, and we have to pick 5 from those cards. It's just 52, we pick 5, we don't care about the order. So these are 5 combinations. Of 52. So we know how to count that because it's 52, choose 5. You don't usually have to, now that we're familiar with it, we don't necessarily have to express what that number exactly is. Okay, because we know how to calculate it. And it's easier actually to leave it as is rather than express it as a number for reasons we'll see. You get some cancellation. Okay, let's say we're interested in the event of getting 1 pair. Okay, what is 1 pair? 1 pair means you're going to have 2 cards of the same rank. And the other 3 cards of different ranks. Okay, so let's be clear. A pair would be something like ace of hearts, ace of diamonds, king of hearts, 9 of spades, 2 of clubs. That's a pair. But something like ace of hearts, ace of diamonds, king of hearts, king of spades, 2 of clubs is not a pair because it's actually 2 pair, right? You have a pair of aces and a pair of kings. The first hand is a pair of aces. All right. So how many ways are there to do this? So it's actually a little tricky to count, but how might we go about counting it? Well, first we want to figure out what pair are we going to deal with. So we're going to be a pair of one of there are 13 ranks. So we have to pick 1 rank. There are 4 cards within each rank, right? For each suit, 1 of each suit. So from the 4 cards in that rank, we have to pick 2 of them. Okay. Now, to get a pair, we then have to pick 3 cards, each of a totally different rank. There are 12 ranks left, right? We don't want to pick from the rank that we already picked. And we need 3 different ones. And for each one, we have 4 possible choices, 1 from each suit. Okay. So what is the fraction of pairs to total outcomes? It's this number, this value here over this value here, which comes out to be about 0.423. So about 42.3% of poker hands are actually pairs. Okay, let's think of another one. Let's say that we want a full house. Now, a full house is 3 cards of the same rank and the other 2 cards are of the same rank, but the 2 ranks are different. So, for example, ace of hearts, ace of clubs, ace of diamonds, king of hearts, king of spades is a full house. How many full houses are there? Well, same logic. Okay, we need to pick the rank that's going to have 3 cards drawn from it. There's 13 ranks. Of those 13, once we have a rank picked, there are 4 cards of that rank. We're going to have to pick 3 of them. Okay, now to pick the remaining pair, we have to pick a rank of the remaining 12. Okay, and then once we have that rank, we have to pick 2 of those cards as 4 choose 2. Turns out about 1 in 700 or 1 in 700 poker hands are full houses. So using poker hands is actually a good way to practice combinations because it's actually we've gone through them a little quick here, and we went through them in a way that made it look easy, maybe, but it's really not easy. And so it's good to work through the exercise of counting how many possible combinations there are in every different type of poker hand. And we'll leave that as an exercise. Okay, so that was this section. We talked about permutations and combinations. So a lot of times we're interested in events that are described by picking from some set of possible outcomes and either considering them in order or unordered. When we think of them in order, we're talking about an ordered arrangement, which is a permutation. When we're thinking out of order, an unordered collection, which we call a combination. So here we've spoken about how to count these in terms of what are called the binomial coefficients. This can be extended even further to what are called multinomial coefficients, and we're going to talk about that in the next section.